right, hello, and welcome to our second lecture of the semester. I hope you all had a good weekend. I had a good one, but a tiring one because I was camping with a 3-year-old, which I don't know if you've ever done this, but it is exhausting. Excuse me. So, anyways, the reason why I bring that up is twofold. One, our song of the day is "Jailhouse" by Sublime. We were camping out near the coast, and so whenever I'm near the ocean, Sublime is just a go-to for me. So you can hit that up. You can hit that link in our description of this video. It'll also be on our course playlist on Spotify, which you can also find a link in the description. The second reason why I bring that up is because if you have emailed me over the past 4 days, I have been off the grid. And so you will be getting a response back from me today. I've got a pile of them, and so I'm going to be moving through, getting back to everybody. So I appreciate your patience and know that you will have a response waiting for you in your inbox. All right, so we left off last lecture talking about significant figures. And last lecture, we ended talking about how to identify the number of significant digits in a number. And we're going to pick up with a few examples just to refresh our memories, get us back in that zone, that way of being. Because again, at the end of last lecture, I emphasized that every answer you give in this class, every calculation you do, there are 3 components to getting full credit, and those components are: your answer needs to have the right value, right? It needs to be the correct number, but it also needs to have the correct units, right? Units are just as important as the value, and then it needs to have the correct number of sig figs. So again, if you do not get these down, then you will hemorrhage points on the when you take exams. So anyways, that's why we're going to invest some time practicing for all of these next examples. Let's identify the number of significant figures. Excuse me. Identify the number of significant figures in each number that we're given. So first, let's go with, okay. Let's go with 30.040. All right, now the 3 rules for significant digits. When it comes to identifying the significant digits in your number is all non-zeros are significant. So the 3 and 4 are significant by default. Next, any non-zero, so zeros can be significant under 2 circumstances. The first is any zero that is both to the left of the decimal and at the end of the number is significant. And you can see that this 0 here is both at the end of the number and, sorry, I said to the left of the decimal, the end of the number to the right of the decimal. That's this 0 right here. So that 0 is significant. A 0 can also be significant if it is in between significant digits. And you'll notice that these 2 zeros are in between 3 and 4. And being sandwiched between significant digits makes these 2 zeros significant as well. So 30.040 has 5 significant figures. All right, let's do another example one that uses scientific notation. Actually, we'll get to scientific notation in just a minute. Let's do a couple more. Let's do let's do 40,000. Well, we know that every non-zero is significant, so our 4 is significant, and a 0 is significant under 2 instances. First, if it's at the end of the number and to the right, of the decimal, it's significant. You'll notice this 0 is at the end of the number, but it's not to the right of the decimal, so it's not significant. Finally, a 0 can be significant if it is in between 2 significant digits, and this number is not, doesn't have any zeros between significant digits. So 40,000 has 1 significant figure. How about 40,000.0? All right, how many significant figures will this number have? Well, we have 1 non-zero digit, that's the 4. With 40,000.0, we do have a number, a 0, that is both at the end of the number and to the right of the decimal. So this 0 is significant. And then you'll notice that these zeros, 1, 2, 3, 4, these 4 zeros in between our 4 and our terminal 0 are between 2 significant digits, so they are all significant. So 40,000.0 has 1, 2, 3, 4, 5, 6 significant figures. Right now, I have a question for you. So we see that you could write 40,000 with 1 sig fig, 40,000.0, which still has the value, a value equal to 40,000, has 6 significant figures. And we could tack on any number of zeros to the end, right? We could do 0.00, and this would have 7 significant figures because we've got our 0 at the end to the right of the decimal, and our 4 making the remaining zeros in between all significant, right? We could go 0.000 and keep growing this number. But I want to ask you about this space in here. The question that I have for you is this. Can you write the number 40,000 with 2 significant figures? Is it possible? And you might be looking at this thinking, no, clearly not. It's you jump from 1 to 6, and then every number after 6 we can do it by just adding a 0. But it doesn't look possible. And the thing is, you can, but you have to use something called scientific notation. All right, you have to use scientific notation, and that could allow you to write 40,000 with 2 sig figs, 3, 4, 5 even. Anything that falls within this range, you could write 40,000 with that number of sig figs using scientific notation, and I'm about to show you how. Before I do, I need to introduce what scientific notation is. All right, so let's talk about scientific notation for a little bit. First off, scientific notation is a way what it is it to write a number in scientific notation you write the number with the decimal immediately after the first non-zero digit so immediately after that first non-zero digit, multiplied by the appropriate power of 10. All right, that is how you write a number in scientific notation. So for example, if you had the number 101, if you want to write this number in scientific notation, remember we have to write the number with the decimal immediately after our first non-zero digit. Well, our first non-zero digit is 1, which means that we have to have our decimal place immediately after it. The problem is the decimal place in 101 is right here. So we have to bounce this decimal place 2 spaces over if we're going to write, 101 in scientific notation. So in scientific notation, 101 would be 1.01. But the thing is, 1.01 is a different number than 101. So we need to multiply this by the appropriate power of 10. So 101 in scientific notation would be 1.01 times 10 to the second power, because if you multiply 1.01 times 10 to the second, your calculator will tell you that that is 101. So this is the number written in scientific notation. All right, let's say you were asked to write, 0.032 in scientific notation. Well, again, we've got a similar problem. Here, our decimal's here. We need our decimal to be behind our first non-zero digit for this number to be in scientific notation. So we're going to move it 2 spaces over. So in scientific notation, this would be 3.2. But now again, 3.2 is not equal to 0.032. We need to multiply 3.2 by the appropriate power of 10 so that these two are equal. So we're going to multiply this by 10 to the negative 2, all right? And the reason why is because if you multiply 3.2 times 10 to the negative 2, it'll come out to be 0.032. And again, this is our number in scientific notation. Now, I want to point something out to you. Notice that in our first example, we move the decimal 2 spaces to the left, which results in a positive exponent of 10. You go 2 spaces to the left, that's 1.01 times 10 to the positive 2. If you look at our second example, when you move your decimal to the right, your power of 10 is a negative number. It's 10 to the negative 2. So that's something to keep in mind. If you're moving your decimal to the left, your power of 10 will be positive. If you move your decimal to the right, your power of 10 will be negative when you write the number in scientific notation. Okay, Tiana, that is an excellent question. So, and that is actually right where we're going next. This is another key feature for scientific notation. Whenever you're writing a number in scientific notation, it is critical that you maintain the number of significant figures. In other words, the number of sig figs that you start with need to be the number of sig figs that you end with. And so one of the things you can see in in 0.032, this number has two significant figures. We've got our two non-zero digits. This 0 is not to the right of the decimal and at the end of the number, so it's not significant, and neither of these zeros are between significant figures. So 0.032 has two significant figures, and 3.2 has two significant figures. When you're counting sig figs, the times 10 to the power of whatever has no significance. When you're writing a number in scientific notation, all of your significant figure information is in the number that you're multiplying by the power of 10, but the times 10 to whatever power adds no significant figures to the numbers. So you can see that 101 has 1, 2, 3 sig figs, and 1.01 times 10 to the 2 second has 1, 2, 3 sig figs. This doesn't add any. So when you're counting sig figs, you never count the times 10 to the whatever power. You only count the numbers in the digits before. And it's critical that the number of sig figs are the same before and after, before writing in scientific notation and after. Gianna, did that make sense? Let me know and I can go through it again. Okay. So with that in mind, now that you know that your significant figures, if you're writing a number in scientific notation, if you're starting with 3, your scientific notation has to be 3. If you're starting with 2, your scientific notation has to be 2. Now we're ready to use, now that we're familiar with scientific notation, we know that the powers of 10 don't add significant digits to your count, your sig fig count. Now we can tackle our original problem. Can you write the number 40,000? Tiana, you are so welcome. All right, can you write the number 40,000? So here's the $1 million question. Can you write 40,000 with 2 sig figs? And the answer is you can. You can. First step is we're going to take 40,000 and write it in scientific notation. All right, so first off, we identify where a decimal is. We know that in scientific notation, it has to be behind our first non-zero digit. So we need to bump this decimal place over 1, 2, 3, 4 spaces. So in scientific notation, 40,000 would be 4 times 10 to the 4th. Again, we are moving our decimal left, which is why our exponent has a positive value. So 40,000 in scientific notation would just be 4 times 10 to the 4th. But now let's do what the problem is asking, and let's write this thing with 2 significant figures. The way you do it is you go 4.0 times 10 to the 4th. Notice, if you punch this into your calculator, 4.0 times 10 to the 4th, your calculator will tell you that this is equal to 40,000. So it's the same number, but look at the significant digits. 4 is significant, and because this 0 is to the right of the decimal and at the end of the number, it is also significant. So 4.0 times 10 to the 4th has 2 sig figs, and it has the same value as 40,000. So there are going to be several situations this semester where you're going to be doing a problem and you're going to need to write a number with 2 sig figs, 3 sig figs, etc. And the only way to do it is going to be to write that number in scientific notation. So this is not going to be every problem. You're not going to need to turn to scientific notation, but it does need to be a tool in your toolbox to get the correct answer on several problems that'll come out through the course of the semester. All right, so let's take some inventory of where we are today. We've reviewed significant figures. We've looked at scientific notation, how it can help us write numbers with the correct number of sig figs that we thought were maybe not possible, like 40,000. We're going to shift our focus just a little bit and talk about where significant digits come from, all right? Because all of this talk is a little on the abstract side. You might be thinking to yourself, okay, like I get it, he's emphasizing it, he's gonna test me on it, so clearly I have to learn this stuff, but I don't understand why it's significant, right? I don't understand what the big deal is. I'm gonna learn it, he told me to, but I don't see the point. I wanna spend a minute talking about why significant figures matter and where they come from, all right? So the deal is, and you might also be like thinking like, I've taken a lot of math classes and this has never come up. So why, right? I've never run into this in a math course. Why are you making me do math, but with this weird extra thing? There's a reason why you've never interacted with significant digits in a math course. And that's because mathematics is known as an analytical science. And the strict definition of that word, analytical, means that it's purely mental. It exists apart from the real world, and you do not need any real world data to do math. It is pure symbolic logic, which is nuts, and it's awesome. Chemistry is not an analytical science. Chemistry could not exist if a bunch of scientists sat around and thought up things and made proofs and theorems and all that stuff. You can't get chemistry from that. You can get math. You can get all of math apart from the physical world that exists. But you can't get chemistry. Chemistry is a physical science, which means that the data that we have, that we've built this system of understanding and explaining the world around us, doesn't come from our head. It comes from observation. It comes from looking at, seeing, observing, and measuring the world around us. And that measurement is key. All right, that is where significant figures come from, is through measurement. And let me show you what I'm talking about. So let's talk for a little bit about measurements and significant figures, because that is the secret origin right there. All right, so let's consider let's say we have a ruler. I'm gonna do my best to space these out as nicely as possible. All right. Okay, sorry. let's go. Let's say this is 0, 1, 2, 3, 4, 1, 2, 3, 4, 5. And we'll call this 1 centimeter, 0 centimeters. So this is 1.2, 1.3, 1.4. Oh, what am I doing here? This is 1.4, 1.6. Oh, wait. What am I doing here? Hang on. Not 1. It's point. 0.2, 0.4, 0.6, 0.8. And there's 1. I should be even more precise than that. 1.0. Centimeters. All right. So we've got this ruler, and let's say we want to measure a piece of string. All right. And let's say this piece of string is that long. All right, let's say we've perfectly lined it up with our 0 mark. I know my drawing's a little sloppy, but let's say it's dead on, 0 centimeters. And I ask you, how long is this string? How long is it? Well, we're in the middle of a bit of a rock and a hard place here, because you'll notice that the string is clearly longer than 0.8 centimeters. If you told me that this string was 0.8 centimeters long, I could say that's not correct. It's longer than that. But the other problem is this string is shorter than 1.0 centimeters. If you told me, oh, the string is 1 centimeter, also not correct. I can see that it's shorter. I can see than 1.0. I can see that it's longer than 0.8. So what is it? Well, the answer is we're limited by the instrument we're used to make this measurement. The answer is this is going to be this string is 0.8 something centimeters. It's not 0.8 centimeters, it's 0.8 and some extra. Right? I'm going to call this, it looks, I don't know. I'm going to call this 0.8 centimeters. Oops. But the reality is, we have no idea what this is. That last digit in this number is uncertain. All right, it is called the uncertain digit because it falls in between measurements. It falls in between where we have lines marking off how long something is. So it's our best guess. The thing is, the last digit, or I should say, the last significant digit in any number is called the uncertain digit because it is our best guess. Oops. It's called the uncertain digit because it's our best guess based on the device that we're using. All right. Now, if we use a more precise instrument, we can get a more precise reading. So if you used a ruler that had more markings in between, you could get a more exact thing. But guess what? It would still fall in between where the in between a couple markings, and you'd still have to guess at that last digit. And you'll notice with this uncertain digit, no matter where this falls in between 0 and 1, any number is going to have the same number of decimal places. We're going to have 2 significant digits, no matter how long this string is. All right. I want to point one thing out. So let's say we're doing the same thing. We've got a string, and let's say we start dead on 0. And let's say that we're like, boom, spot on 0, that we end exactly at 0.6. You might be tempted to say that this string was 0.6 centimeters. And you can say, Josh, look, it's dead on 0.6. Like that's what it is. And it's true, but here's the thing. Even when you're measuring something and it falls exactly on one of the markings on your instrument, you still need to include the uncertain digit. And if it's dead on 0.6, then the number you record is 0.60 centimeters. All right, you will always have that uncertain digit. Even if it's dead on a marking, then you just add a 0. Because the device that you're measuring on will always give you 2 decimal places no matter what. So even if you're dead on a measurement, you write 0.6 and then add a 0. All right, now this is where significant digits come from. The number of significant digits in your number are determined by the precision of the instrument that took that initial recording. And when we keep track of significant digits as we do calculations, it's to preserve the precision, or you can think a crude way of thinking of it is accuracy, preserve the accuracy, the precision of the original measurement. So that's why they matter, because all of our information in chemistry is based on measured and recorded data, and the precision of that data is reflected in these numbers, significant digits. So that's why they matter so much. And if that's not enough to persuade you of their significance, know that they're going to be on every test in the final. So every test except for the prereq exam, that has no sig figs. Every test after that, though, sig figs are coming at you. All right. Let's talk about the rules for sig figs. Starting with addition and subtraction. Okay, great question. Excellent question. Here. Let's drop back real quick. So the question coming in is what would be the scientific notation for 0.6 centimeters, 0.60 centimeters. All right, so first off, we need to move our decimal so that it comes after our first non-zero digit. So our decimal would need to be behind 6, all right? When it comes to the power of 10 that we're going to use, we moved our decimal space 1 over and we moved it to the right, which means it's going to have a negative sign. So it's going to be times 10 to the negative 1, right? Because we only moved that decimal place over 1. So in scientific notation, it's going to be 6 times 10 to the negative 1. But then finally, well, actually, there's two things. First, 0.60 has 2 sig figs. So when we write this number in scientific notation, we also need to make sure that we have 2 significant digits. So we need to write it as 6.0 so that the number of significant digits are maintained. Finally, the last thing you look to is your units. If you have a number that begins with units, when you write it in scientific notation, you must include those units as well. So all told, 0.60 centimeters in scientific notation is going to be 6.0 times 10 to the negative 1 centimeters. So that is our number in scientific notation. Let me know if that makes sense. Excellent question, by the way. Great application of what we were just talking about. All right, so we're going to transition into looking at how to apply the rules for significant figures and how to preserve sig figs as we do mathematical operations, specifically addition and subtraction, as well as multiplication and division. And we're going to begin with addition and subtraction. All right. So, let's see. Yeah. Tiana, great question. So Tiana's question is, do we put our answer in scientific notation only if I specifically ask? And yes, that is one instance. If I specifically ask for an answer in scientific notation, it's got to be in scientific notation. The second time, and you'll see how this will arise when we do a few of these examples, is sometimes you'll be doing a problem where your answer must have like 2 sig figs. And let's say your answer is 40,000. In that instance, you have to write the number with 2 sig figs, but 40,000 only has 1. So that would be the second situation where you have to use scientific notation. That is, if you have a number that needs a specific amount of sig figs that number doesn't have, you'll be able to do so by using scientific notation. And you'll see that'll come up as we move through these examples. So when you look at the rule for addition and subtraction and significant figures, the rule is this. The answer's precision must be the same as the least precise number used in the calculation. All right. So our answer's precision must be the same as the least precise number used in the calculation. Now, there are two times where this word has cropped up, precision and precise. What exactly do we mean? So to understand this definition, we need to look at what precision is in a technical sense. All right. And precision, the precision of a number, is determined by the last significant figure in the number. And this is the critical part. The further to the right it is, the more precise the number. All right, now this is the type of thing that is much easier to see with examples than with words. So, for example, if you were to compare the number 10.37 versus the number 0.981, if I were to ask you which is more precise, remember, precision is determined by the last significant figure in the number. And 10.37 has its last significant digit in the second decimal place, the hundredths place. 0.981 has its last significant digit in the thousandths place, right, the third decimal place. And we said that the further to the right your last significant digit is, the more precise your number is. So 9.87 is more precise. All right, because its last significant digit is further to the right than 10.37. Let's do another example. Let's compare 2,370 to 2,400. All right, you'll notice that 2,370 has its last significant digit in the tens place. 2,400 has its last significant digit in the hundreds place, which makes 2,370 more precise because its last significant digit is further to the right. It has its last significant digit in the tens place, whereas 2,400 has its last significant digit in the hundreds place. So with that in mind, let's take a look again at the rule for applying sig figs, maintaining sig figs, when you do addition and subtraction. It says the answer's precision must be the same as the least precise number used in the calculation. All right, so now let's apply this. Let's actually do a few examples where we use this rule. So let's go ahead and start with 14.6 plus 22. All right, if you do this math, if you punch it into your calculator will tell you that your answer is 36.6 0.6. All right, and that is your correct value. But you need to ask, every time you hit enter on your calculator, it'll give you the correct value. You have to ask, how many significant digits should this number have? All right, now, to determine our number of significant figures, we have to look at the last significant digit in each number. So when we look at 14.6, its last significant digit is in the first decimal place. When you look at it's just 22, its last significant digit is in the ones place. All right? Now, the rules for addition and subtraction are that our answer must have the same precision as the least precise number. 22 is less precise because its last significant digit is further to the left. 14 is further to the right, 14.6 is further to the right, which makes it more precise. So because 22 is less precise, our answer must have its last significant digit in the same place as 22. So our last significant digit for our answer needs to be in the ones place, which means we need to round. And when we look over at 0.6, 0.6 is going to round up, making our 6 right here, and 36, into a 7. So the correct answer with the correct sig figs here is 37. All right, that is the answer. All right, let's do a couple other problems. Let's do 3,700 plus 50. All right. If you punch this into your calculator will tell you that the answer is 3,750, but we have to ask, what's the sig fig situation? All right, 3,700 has its last significant digit in the hundreds place. 50 has its last significant digit in the tens place. In this example, 3,700 is less precise, and so our answer has to have the same precision as 3,700, meaning we need to round to the hundreds place. 5 rounds up, turning our 7 into an 8. So our correct value with the correct sig figs here is going to be 3,800. All right, let's do one last example. 1.057 minus 0.943. Punch this into your calculator. Let's see, this is, so minus 3 is 4. 1. Our answer would come out to be 0.114. You'll notice that for both of these numbers, their last significant digit is in the third decimal place. And you'll notice our answer actually has its last significant digit in the third decimal place, so no rounding is necessary here. Our final answer will be 0.114 because that has the correct number of significant figures. All right. So those are the rules for addition and subtraction. You look at the position, the place value of the last significant digit in the number, and you have to round your answer so that it reflects that precision. All right. Now, the good news is, of the two sets of rules, so there's a set of rules for addition and subtraction, there's a set of rules for multiplication and division, and I find that I've found over the course of my career that the rules for addition and subtraction tend to be harder for students to remember. But the rules for multiplication and division tend to be a little bit easier. So if you're tracking with that one, this one is going to be a little less complicated. So here are the rules for multiplication and division. The number of sig figs in the answer must be the same as the number or I should say as the value with the fewest sig figs used in the calculation. Okay, so with multiplication and division, it's a little more streamlined. You'll notice with addition and subtraction, we used precision in our definition, then we had to define precision and figure all that out. Multiplication, division, it's more straightforward. You look at the number of sig figs in each number, whichever one has fewer sig figs, that determines the number of sig figs your answer can have. All right, so let's do some examples. Let's do 271 times 13. I can't do this in my head. I don't know if you can. If you can, power to you. Your mind is stronger than mine. But I'm going to punch it into my calculator. My calculator is going to tell me, or is telling me, that the answer is 3,523. Now that's the correct value. We need to determine the correct number of sig figs. 271 has 3 sig figs in it. 13 only has 2. And you always, for multiplication and division, roll with the fewest number of sig figs. So our answer can only have 2 sig figs. And 2 is going to round down. So the correct value with the correct number of sig figs will be 3,500. All right, that is the correct answer with the correct number of sig figs for 271 times 13. All right, let's do another example, possibly a more upsetting example. Let's do 11 times 3. You punch this into your calculator. 11 times 3 is 33. 11 has 2 sig figs. 3 only has 1, and you have to roll with the fewest when you're multiplying. So you count off your first sig fig. 3 rounds down. So our answer to 11 times 3, when you apply the rules for sig figs, is 30. Now, this is upsetting, deeply upsetting. This is where in lecture, a lot of students go, okay, this is garbage because I know 11 times 3 is 33, and here's a professor telling me that 11 times 3 is 30. And this is where a lot of students check out. But I would like to point this out to you. If you want 11 times 3 to be 33, may I submit to you that you need to use a more precise number in your multiplication. You need to measure that number 3 with a better ruler so that you know for a fact that it's not just 3, that it's 3.0. Should you choose to do this, your mathematical intuition will be rewarded. Because 11 has 2 sig figs and 3.0 has 2 sig figs, which means that your answer is allowed to have 2 significant figures, and 11 times 3.0 does indeed equal 33. Okay, that's the thing to remember. These sig figs aren't made up, they come from measurements. And so if the numbers aren't working out the way you want them to, that means that you need to make some more precise measurements with a more exact instrument. All right. So that's addition, subtraction, multiplication, division. What happens when you have both addition, subtraction, and multiplication, division in your problem? All right, let's talk for a minute about mixed operations. All right. So let's talk about mixed operations. What happens when you have both addition, subtraction, and multiplication and division in your problem? And the answer is you follow your regular algebraic order of operations. You just follow your regular algebraic order of operations. For example, if you had 12.0 plus 8.0 divided by 14.22. The way you do this problem is first step, you do rules for addition, apply the rules for addition, and then second step, you do rules for division. All right, so you kind of take it one chunk at a time. First, we're going to apply the rules for addition, subtraction. Second, we're going to apply the rules for division. And that's how you get to the correct answer. So some students get confused here. They think, oh, do we just apply division rules? Do we just apply addition rules? You've got to apply them in sequence. And I'm about to show you how one step at a time. So first, the rules for addition, subtraction. 12.0 plus 8.0, if you punch this into your calculator will tell you that the answer is 20, but you have to ask, what are my rules for sig figs? One of the things you'll notice is that 12.0 and 8.0 actually have the same precision. they both have their last significant digit in the first decimal place. That means that our answer must have its last significant digit in the first decimal place. So 12.0 plus 8.0 is not 20, it's 20.0. We need that significant digit in the first decimal place. All right, now the next part I'm not going to do in my head because I don't know how many times 14.22 goes into 20. So this turns out to be, the calculator's telling me 1.40646976, and the number keeps going. The number keeps going, but frankly, we don't have to because we just did division. And when you do division, your answer has to have the same number of sig figs as the number that you used in the calculation with the least. And you'll notice that our numerator has 3 significant digits. Our denominator has 4. So we've got to roll with our numerator because it has 3. So you count off your first 3 spaces, 1, 2, 3. 6 is a number that rounds up. And so our correct answer with the correct sig figs will be 1.41. All right, and we got to this answer with these correct, with the correct sig figs by applying first the rules for multiplication, first the rules for addition, which is in our numerator, followed by the rules for division. All right, let's do another example. Okay. How about so 18.9 times 0.037 plus 42.0808. All right, now we gotta follow the normal order of operation, which means first we're going to apply the rules for multiplication, and second we're going to apply the rule for addition, because you always hit what's in your parentheses first. All right, those are your normal algebraic order of operations. So, again, I don't have a brain that can just do 18.9 times 0.037, but that is why we have calculators. So 18.9 times 0.037 comes out to be 0.6993. Now, it's not enough to just write our answer. We have to ask how many significant digits should our number... Sorry, no, we have to look at the precision. No, sorry. Tripping myself out here. We just did multiplication, which means we have to ask how many significant digits can our answer have. 18.9 has 1, 2, 3 significant digits. 0.037 has 2. We got to roll with the fewer. So our answer can have 1, 2 sig figs. Now, I'm not going to round right now. I'm not going to round because we're not at the end of the problem. You always save your rounding to the very end. But what I am going to do is put these two lines here to remind myself that this number has two significant figures, but I'm going to wait to round to the very end. All right, now we need to add 42.0808 to this number. And again, I'm just going to punch this in, plus, so 0.6993 plus 42.0808. All right, this comes out to be, the value is 42.7801. All right, now I have to ask, what is the precision of my answer? 0.6993 has a precision that only goes to the second decimal place because that is the position of my last significant figure. 42.0808 has its last significant digit in the fourth decimal place. And so our answer must have the same precision as the least precise number, which in this case is our first one, because it's precise to the second decimal place. So I need to round to the second decimal place. 0 rounds down. So my correct value with the correct number of sig figs will be 42.78. And again, we got here by first applying the rules for significant figures for multiplication, then applying the rules for significant figures for addition. That's what got us to this final answer. All right. So that is, at this moment in time, you have seen everything that can be thrown at you sig figs wise. You've seen addition, subtraction, multiplication, division, and then mixed operations. All of these rolled up together will encompass basically all the instances of sig figs that you'll run into this semester. What I'll say is we're going to do plenty more examples of this because it's basically going to be every calculation that we do together. We're going to be applying the rules for significant figures. So we're going to get a lot of reps in with this stuff as we move through the course. But we're going to now shift. We've been looking explicitly just at significant digits. Let's shift our focus to unit conversions. All right, at this point in time, we have covered, we said that every correct answer has three components, right? There's the value, it's the number, the significant figures, and the units, right? And you have to have all three correct to pull down full credit. And we've spent a lot of time, right, talking about significant digits. We know what the correct value is. Let's spend some time talking about unit conversions. All right. In the metric system, we use prefixes. All right, and I wrote these up last lecture to kind of give you, because I said you have to have these things memorized, and I'm going to just reiterate them here because they are that important. So in the metric system, we use a system of prefixes to modify the units that we're using. So the basic unit, for example, for mass is grams, length is meters, volume is liters. But then we can modify those units with these prefixes to specify them. So if you're dealing with a long distance, you'll measure them in kilometers, not meters. Because, for example, adding that prefix kilo, and the name is kilo, the prefix is K, means 10 to the third. So 1 kilometer, 1 kilometer is 1,000 meters. 1 kilogram is 1,000 grams. So these units are more flexible, and the conversions are base 10. So it works nicer with our mathematics. And these are the prefix names that you need to know. Again, I wrote these out last lecture, but I want to reiterate them here. Centi, it has a prefix of C, means 10 to the negative 2. So, for example, for a meter, you'll have 100 centimeters fitting inside that meter, so it's a smaller unit. Milli is M, and it is 10 to the negative third. Micro is mu, which is the Greek letter for M, right? Different than, M was taken for milli, so micro got the leftovers from another alphabet. It's 10 to the negative 6. And nano is N, it's 10 to the negative 9th. Again, I can't iterate this enough. You need to memorize these dudes. You need to have them memorized. Because I do provide equation sheets for the exams that I give, but I do not give these because you just need to know them off the top of your head. Okay, so let's see. All right, so these are the names, the prefixes. Let's get some practice doing these unit conversions. I should mention one thing before moving on. And that is, well, actually, I'm gonna get a new slide. So conversions within a system of measurement are exact. In other words, they do not affect the sig figs of a calculation. All right, so for example, if I asked you to convert 50 kilometers to meters, all right, here's how you'd go about doing it. You want to set up what is known as a unit conversion, which is a ratio. You want kilometers to cancel, so we're going to put kilometers in the denominator. You want to be left with meters, so meters goes up in the numerator. Then you have to ask yourself, how many meters are in 1 kilometer? And the answer is the unit multiplier from that table. So kilo means 10 to the third, so 1 kilometer will have 10 to the third meters. Algebraically, you'll notice that kilometers cancel each other. You're left with meters, which is good, right? Because we're trying to convert from kilometers to meters. So now you have to punch into your calculator 50 times 10 to the third, which your calculator will tell you is 50,000. Now remember, 3 things. make an answer correct. There's the value, which we have here, 50,000. There are the units, which we have right here, meters, and then there are the sig figs. And you'll notice that 50 has one significant digit, 50,000 has one significant digit. So your sig figs here are correct. So 50,000 meters is equal to 50 kilometers. Now, you may be going, Josh, why didn't you look at your unit multiplier to see if that would affect your sig figs? The reason why I didn't is because we are converting within a system of measurement right now. We're in the metric system. Meters is a metric system unit, kilometers is a metric system unit, and the relationship between meters and kilometers is not a measured relationship. It is a relationship based on a definition. 1 kilometer is defined as being 1,000 meters. So if you're going from metric unit to metric unit, the unit conversion will never affect your sig figs. If you're going from English unit to English unit, that unit conversion will never affect your sig figs because, for example, 1 foot is defined as having 12 inches in it. That's not a measured quantity. It's exact. It's based on a definition. When you are going from English unit to metric unit, that is when English unit to metric unit or metric unit to English unit, that's when your sig figs, your unit conversions will affect your significant digits. All right? So let's go ahead and do a few more unit conversion problems. We'll stay within the metric system. Let's convert let's convert 5.5. Oh, no. Hang on. Let's convert 5.0 liters to milliliters. All right, so your first step when you're doing a unit conversion is you want to set up your ratio. We want liters to cancel, so that goes in the denominator. We want to be left with milliliters, that goes in the numerator. And now that we've set those up to cancel, we need to add our unit multipliers. Now, 1 milliliter, milli means 10 to the negative third. So you always put a 1 by your modified unit. 1 milliliter is 10 to the negative third liters. And now liters cancel. We punch this into our calculator. When you do, 5.0 divided by 10 to the negative third comes out to be, your calculator tells you that your answer is 5,000. Your unit is milliliters, so we've got the correct value, the correct units. Now we have to ask about sig figs. 5.0 has 2 sig figs, and 5,000 only has 1. You might be thinking, okay, no problem. Let's add. What if we added a 0.0? The problem there is if you add a 0 behind the decimal place, now you have 2 significant digits with 3 in between. This 5,000.0 has 5 sig figures. That's not going to work. Well, 5,000 has 1, 5,000.0 has 5. How do you write it with 2 sig figs? The answer is scientific notation. We need to use scientific notation to write 5,000 with 2 significant digits. So this is an instance, this is an example of what I was talking about earlier, where sometimes I'll ask you, write this problem and this answer in scientific notation, and you have to. But sometimes you'll get an answer. The correct answer is 5,000. The correct sig figs is 2. The only way to write 5,000 with 2 sig figs is by using scientific notation. So let's start by writing 5,000 in scientific notation, and then we can, once it's in scientific notation, make sure it has 2 sig figs. So we're going to start by taking our decimal and moving it behind our first non-zero digit. So we got to move it 3 spaces to the left, which means we're going to have a positive exponent of 10. So this is going to be 5 times 10 to the 1, 2, 3. Right, and again, because we're moving to the left, it's positive. Now, we need to write this with 2 sig figs. So we add a 0 behind our 5 because 5.0 has 2 sig figs. Finally, you have to remember that this is 5.0 times 10 to the third milliliters. And this is our correct answer. Correct value, correct units, correct sig figs. All right, converting 5.0 liters to milliliters. Let's do another example. Let's go 420 nanometers. Oops. To meters. All right, so first up, we need to set up our unit conversion so that nanometers cancel and we're left with meters. Next, we have to look at our unit multipliers from that table that I wrote up earlier. You got to have this thing memorized, but at the beginning it might be helpful to have it out as a reference. 1 nanometer is 10 to the negative 9. That is the unit multiplier. Nanometers cancel. And now, when I punch this into my calculator tells me that the answer is 4.2 times 10 to the negative 7th. My calculator just punched it in scientific notation. But we have to ask ourselves, are our sig figs correct? 420 has 2 significant digits in it. 4.2 also has 2 significant digits, so my sig figs are spot on. My unit is meters, and this is my correct answer. 4.2 times 10 to the negative 7th meters. That is correct value, correct sig figs, and correct units. That is getting full credit as an answer. All right. So we've got a couple more examples to go through. One of the things you'll notice is we did liters and milliliters, meters and nanometers, always going from a modified unit to a base unit. When I say modified unit, I mean a unit with a prefix. But let's look at an example where we convert from a unit with a prefix, like, for example, let's convert 52 milliliters to microliters, right? And here we've got 2 modified units because we've got milliliters and microliters. One of the things you should be aware of is that table that I put up earlier that we've been using here with those unit modifiers are only good for converting between modified units and the base unit. So we could use that, for example, to convert from milliliters to liters, or we could convert from microliters to liters, but it can't go directly. You can't use those unit multipliers to go directly from milliliters to microliters. When you are asked to convert from a modified unit to another modified unit, you have to do so in a two-step process. So the first step, because we don't know how to convert milliliters to microliters, but if we had liters we could convert to microliters, your first step is to go from modified unit to base unit. So we would want to cancel milliliters, convert to liters, and then your second ratio is going to convert from base unit to the desired modified unit, so from liters to microliters. For our first ratio, 1 milliliter has a unit modifier of 10 to the negative third. 1 microliter has a unit modifier of 10 to the negative 6. And you'll notice milliliters cancel milliliters, liters cancel liters. The only unit left standing is microliters, which is great because that is the unit that we're after. When you punch this into your calculator will tell you that your answer is 52,000. Right? When you look at your significant digits, 52 has 2 sig figs, 52,000 has 2 sig figs, so there's nothing to modify there. So the last piece that we need to add here is our units, because we have the correct value, the correct sig figs. Now we need the correct units. 52 milliliters is equal to 52,000 microliters. So that is how you handle unit conversions going from modified unit to modified unit. You're going to need to use two ratios. The first, to convert from your modified unit, to cancel your modified unit, leave you with a base unit. The second, you will cancel your base unit to go to your second and desired modified unit. So modified to modified, 2 steps, 2 ratios. Modified to base, you just need 1 ratio. All right. Now, we've been doing all of these unit conversions within the metric system. I do want to do one example of going metric to English. So let's take 458 centimeters, actually, meters, and convert this to feet. This is going to be a multi-step process. Hang on. I want to alter this slightly. We're going to say 458.2 meters to feet. And you should note, I will not be providing metric unit conversions on the exam, but any conversion that does go from metric to English, I will give you. So 1 inch is equal to 2.54 centimeters. And that is information I will provide you. Now, something you should know is this unit conversion is not exact. This unit conversion is measured, which means that its significant digits they won't always, but they can limit your calculation, all right? Because inches and centimeters are 2 different systems of measurement, and so it's not a definition. It's not there's exactly 2.54 centimeters in 1 inch. We had to measure it, and the precision here matters. So keep that in mind as you do this calculation. Now, let's look at it. what am I doing here? 458.2 meters. Now we know that our key unit conversion takes us from centimeters to inches. We can get from inches to feet. So our first step needs to be getting from meters to centimeters. We want meters in the denominator so that they cancel and we're left with centimeters. We know that centi is 10 to the negative 2, so 1 centimeter is 10 to the negative 2 meters. Meters will cancel. Our next unit conversion needs to cancel centimeters and leave us with inches. And that unit conversion we get right here. 1 inch is 2.54 centimeters. Centimeters cancel. Finally, our last unit conversion will take us from inches to feet. And 1 foot is 12 inches. Inches cancel. And now, feet is the only unit left standing, which is good because that is what we were trying to convert to. Now we're ready to crunch some numbers. Let's see. 458.2 divided by all right. So this is coming out to be. My calculator is telling me that my value is 1,503.280,839,895. Let's look at the number of sig figs we can keep. All right. Our initial quantity has 4 sig figs, but you'll notice that our unit conversion to go from centimeters to inches, which is measured, it's not exact, is going to limit us to 3 sig figs. So we can only keep 1, 2, 3, and 3 is going to round down. 3 rounds down, making our answer 1,500. But we have a problem. 1,500 only has 2 sig figs, but we need 3. We need 3 sig figs. So what are we going to do? The answer is, as always, scientific notation. We've got 2 sig figs, we need 3. If we added a 0.0, it would have too many, it'd have 5 sig figs. So we need to convert 1,500 to scientific notation. We find our decimal and move it behind our first non-zero. So this will be 1.5 times 10 to the, let's see, we went 1, 2, 3, 10 to the third. And we need 3 sig figs, so this is going to be 1.50 times 10 to the third, correct value, correct sig figs. We need the correct units, which are feet. So 1.50 times 10 to the third feet is the correct value, the correct units, and the correct sig figs. Here again, you can see that this is a problem that necessitates the use of scientific notation in order to write our number with the proper amount of sig figs. All right, so this is the thing that comes up kind of again and again and again. So you should keep an eye out for it. All right. We have two last things to talk about in this chapter. The first of which is going to be an extension of everything that we've done up to this moment in time. And then the second we may not get to today, we'll see. But we've got to talk about density and temperature, and then we will be done with chapter 2. So let's dive into density. All right, density is a ratio of mass to volume. All right, density, which is represented with a lowercase d. So density, oops, there we go, is equal to the mass of a substance divided by its volume. All right, and the symbols used, density is a lowercase d, mass is a lowercase m, and volume is a v. So density is equal to mass over volume. A typical unit, so these could be any units, any mass unit, any volume unit. You can have a density. Density can come in many different types of units. But typically, what you see here in the numerator is masses, typically in grams, but can be in kilograms. The volume, really, this varies more widely than the numerator. Usually the numerator is grams, but the volume, the denominator could be milliliters, could be liters, but it really could be any density, any volume unit. So you see densities will often be expressed in grams per milliliter, or you'll see grams per liter, or sometimes you'll see kilograms per liter. You could see micrograms per microliter. There's all sorts of, any mass unit can be in the numerator, any denominator, any volume unit can be in the denominator. It's just all over the place. But the most common ones that you're going to run into are going to be grams per milliliter, grams per liter, are going to be the ones you see the most. Sometimes you'll see kilograms per liter, but mass over volume is a density. All right, and this is the equation for density, which you're going to get a lot of reps in. This is an example of something that I would put on the equation sheet, so you don't have to memorize any algebraic formulas, any algebraic equations. For this class, I'll provide all of them to you on the cover sheet, of your exam. Now, let's do some examples. What is the density of a substance in grams per liter that has a mass of 15 grams and a volume of 44.0 milliliters. All right. Now, you may be tempted to dive right in and go, okay, well, Josh, well, first off, actually, I'm going to take a step back. Whenever you're asked to solve a problem in this class, there's a method to doing so. If you follow this method, you will be able to tackle not only problems that you have seen, but problems that you've never seen before. And I'm gonna make you a promise right here, right now. I promise you that on the exams, I'm gonna ask you questions that I have never shown you in class. It's not gonna be every question. Some of them you'll have seen before. Some of them will be similar to homework problems. Some of them will be similar to lecture examples. But I guarantee you that you are going to face at least one problem on every test, sometimes more than one, that you've never seen it before, and I've never done it for you, and you've never done a problem like it. This can be terrifying for a lot of students. The reason why I do this is because I'm not interested in your ability to memorize doing a type of problem that you've seen me do or that you've watched someone else do. I'm interested in your ability to think critically. I want to know, can you take a set of information, maybe in an unfamiliar configuration, and use logic to find the answer? There's no way to prepare for this from the standpoint of doing a problem like it, because if it's a problem you've never seen before, you've never seen it before. But if you use this method I'm about to show you and apply it to a problem you've never seen before, you'll be able to get to the right answer, even though it's your first time doing it. So I wanted to stress this method as we move through. So the first thing you want to do, identify what you are trying to find. In this problem, what are you trying to find? And you'll notice it's right here. What is the density? All right. So you are trying to find density. And density has an equation. Density is equal to mass over volume. This is clutch because you're after density, which means if you can find the mass and you can find the volume, then you will be able to calculate the density. That's step one. Step two, let's look at what we're given. So what is the density of a substance in grams per liter? So we're given that the units need to be grams per liter. Let's say we're told the substance has a mass of 15 grams. That is the numerator of our expression for density. We've got mass right here. And the volume is 44.0 milliliters. 44.0. That is our volume. So we have our mass, we have our volume, we can calculate density. There's one small hitch before we dive in. You'll notice that we're asked to find the density in units of grams per milliliter, per liter, but our volume is given to us in liters. So we actually need to do a unit conversion before we plug these values into this equation. We need to convert from milliliters, which we'll put in the denominator, to liters, which goes up in the numerator. So 1 liter is 10 to the negative third milliliters. Now milliliters cancel. And if you punch this into your calculator will tell you that 44.0 divided by 10 to the third is 0.044 4. You got to ask yourself, does this number have the correct amount of significant digits? The answer here is no. 44.0 has 3 sig figs. 0.044 only has 2. So we need to add a 0 right here so that we have 3 sig figs. So this is 0.0440 liters. And now we're good to go. We can find our density. Density is equal to mass, 15, grams over volume, 0.0440 liters. So I can't do this in my head. Maybe you can. More power to you. But I need a calculator to crunch these numbers. 55 divided, or sorry, not 55. 15 divided by 0.0440 comes out to be, oops, 340.9090 forever. We don't have to write this forever though, because we've got 2 sig figs in our numerator, 3 in our denominator. We're limited by the fewest because this is division. So you count off your first 2, 0 rounds down. So our density is 340. And now our units are grams per liters, just like we were asked. This is our answer. All right, so take a step back and look at what we did. We were asked to find the density of a substance in grams per liter that has a mass of 15 grams and a volume of 44.0 milliliters. And we deconstructed the problem. We identified what we were trying to find, density. We wrote out what density equals, which the algebraic expression gave us a roadmap for solving this problem. Told us we need mass, told us we need volume. We wrote down the unit specifications, we found the mass and volume, converted the volume so all the units lined up, and then crunched the numbers. This is the template for solving every problem I throw at you in this course. You're going to see me use it over and over and over again, and that's to give you the repetition. I want this to become like breathing for you so that when you get to the exam and you see that question that you've never read anything like it before, you're not going to freak out. You're going to go, I may not know you, but I know how to break you down. All right, that's what we're going for here. We got time for maybe definitely one, maybe 2 more examples. Let's see how this goes. All right. So, let's do another example. Substance with a density of 1.408 grams per milliliter occupies a volume of 18.6 milliliters. Determine its mass in kilograms. All right, first step in any problem is you need to identify what you're trying to find. And this is right here. At the end, we are being asked to determine the mass in kilograms. All right, so not just the mass in any unit, the mass specifically in kilograms. That's what we're trying to find. Let's look at what we're given. All right, the first thing, so I'm reading the problem, a substance with a density. Okay, that's the first thing we're given. We're told that the density of the substance is 1.408 grams per milliliter. Now, I want to give you a tip. This thing is going to serve you well on almost every single problem you do in this class. Anytime you're given the value of a quantity that also has an equation attached to it, like density, it is worth your time to write out the equation for that substance, for that expression, for that quantity under your givens. Density, we're told that the density is 1.408 grams per milliliter. Density has an equation. That equation is density is equal to mass over volume. Here's why you want to write that out under your givens. We've been told to find mass, and check it out. Mass is in this equation, which means that if you know the density and you know the volume, you can find mass. All right? And guess what? We've just written down what the density is. Now we're on the hunt for volume. We go back to the problem and we see that volume, the volume of this sample of material, is 18.6 milliliters. So we know the volume. We can now use this equation to find our mass algebraically. And here's what I'm talking about. Density is equal to mass over volume. We know our density, we know our volume, we want to find the mass of this substance. To find mass, we need to isolate it on one side of this expression. So I'm going to multiply both sides by volume so that volume cancels and we're left with mass all on its lonesome. So mass is equal to density times volume. And we know both of these. Density is 1.408 grams per milliliter, and our volume is 18.6 milliliters. Crunching our numbers now. 1.408 times 18.6 is 26.188. All right, let's look at the number of sig figs we can keep. 18.6 has 3 sig figs. 1.408 has 4. And we got to roll with the fewer of the two, right? So we got to roll with 3. 1, 2, 3. 8 rounds up. So our mass here is 26.2. All right, now let's look at our units. You'll notice milliliters cancel with milliliters, leaving us with grams. All right, so our mass is 26.2 grams, but that is not what we were asked to find the mass in. So we're not quite done. It'd be very easy to write this down to box it, right? Because it's the correct value, correct sig figs. But the units here are not correct. We're asked to find our mass in kilometers, our mass in kilograms. But here, the mass that we found is in grams. So we have one last unit conversion to perform. So what was it, 26.2 grams. We want grams to cancel, so they go in the denominator. We want to find kilograms. They go up in the numerator. 1 kilogram is 10 to the third grams. Grams cancel. You punch this into your calculator, and the answer you get out the other end is 0.0262. When you do a quick significant digit check, you see that 26.2 has 3 sig figs, and 0.0262 also has 3 sig figs. So our sig figs are good. Our units are kilograms. And this is our correct answer. 0.0262 kilograms is the mass of a substance with a density of 0.1408 and a volume of 18.6 milliliters. Alrighty. I'm going to leave us with a bit of a cliffhanger. So rather than rush this last example to get it in before class ends, I'm going to write it out, leave it for you to try on your own. So try this at home, kids. Try it at home, see if you get the correct answer. Come back on Wednesday's class. We'll do it together. You can see if you handled it, or see how you handled it. All right, so let's see here. I'm sorry. The reason why I'm pausing here is I'm trying to think how hard should I make this problem. But you know what? Let's go full metal, right? Let's go as bad as it could be. Give it a whirl on your own. Come back Wednesday. We'll see how to iron it out. All right. Point 402 grams of an unknown metal occupies 0.908 milliliters of space. Part A. Determine the density of this metal Part B, our first two-parter. How many liters actually, sorry, there's a better way to phrase this. Oops. Part B, determine the volume in liters that 58 kilograms of this metal would occupy. All right, that is your part A and part B. It will take, or it would take me, more than 4 minutes to solve this problem. So take a crack at this. Come back Wednesday, and we will do this at the start of lecture. Thanks everyone for popping in. We had a handful of great questions, and look forward to seeing your bright and digital faces in a couple days. And again, if you email me, you'll be hearing back from me today. All right, take it easy, dudes.